Hi everyone. Sorry we can't be in class together today, but I'm hoping this video lecture will be useful to you. We're going to introduce a very interesting, very fascinating topic in quantum mechanics, namely the distinction between two types of particles, one type called bosons and the other type fermions. So what is the distinction and what is it based in? So we said earlier that if you have two particles, then a two-particle wave function can be written like this. Psi A of R1 times psi B of R2. So that is one allowed wave function for the combined system of two particles. We have the product because we want the first particle to be in state A and the second particle to be in state B or psi sub B. The R1 variable refers here to the location of the first particle and the R2 vector refers to the location of the second particle. Okay, so we basically get this product because we want the first particle to be here and the second particle to be there. So we discussed that. Now the problem, though, with this two-particle wave function is that it implies that we can distinguish the two particles. We can say that the first particle is in state psi sub A and the second particle is in state psi sub B. So I'm basically tagging the particles and distinguishing them by their number 1 and 2. Now, this is not a problem for distinguishable particles. You know, this is if the particles are distinguishable, then this is a perfectly fine two-state wave function, two-particle wave function. So if you're, for instance, dealing with an electron and a proton, then there's no problem here. The problem really comes in when you're using two identical particles. So two electrons, for instance. When you look at subatomic particles of the same kind, like electrons, protons, and so on, they are basically indistinguishable. You cannot tell one from another. Okay, they're completely indistinguishable. In classical physics, you can say two things are indistinguishable. I have two cups in front of me that look exactly the same because they were manufactured in some factory to the same specification, but I can still distinguish them because one cup is here and the other cup is there. So by their spatial location, I can still sort of distinguish them. And maybe they're also not completely identical. It's very hard to make a macroscopic object that is identical in every way to another macroscopic object. But in the quantum world, in the microcosm, we can say that all electrons are exactly the same. They have exactly the same rest mass. They have the exact same spin, namely spin 1/2, h bar over 2. They have the exact same charge, negative elementary charge, 1.6 times 10 to the negative 19 coulombs. And then there's nothing more. No more characteristics that could distinguish two electrons. And furthermore, they're described by a wave function. So I can't really even distinguish them by their discrete spatial locations because the locations are also smeared out. So we're basically getting a little bit philosophical here, but you can kind of see that for elementary particles described by a wave function, you really could not distinguish one such particle from another in a very fundamental way. You can't distinguish them because you can't even distinguish them by their discrete locations. And so The short of it is that, to make a long story short, we have to modify this wave function, because the way it's written now up there, we're pretending like we can distinguish them. Okay, and so how are we going to do that? So yes, all electrons are completely and utterly indistinguishable, more so than any two objects in the classical world, in our world. Okay, so the mathematics has to reflect that. And so here's my proposal. The actual wave function, the actual two-particle wave function, psi of R1 comma R2, should read like this. Okay, and there you have it. There's one piece of it that is the same as before, but then there is a second piece added on, right? A second piece added on, this piece here. And you notice that it basically just switches the A's and the B's. What that means now is that the first particle is in state psi B, and the second particle is in state psi A. Okay, so we can't really now say that the first particle is in A and the second particle is in B, because we've added another part to the wave function where it's exactly reversed. Okay, and so you can show that if you switch the locations of the two particles, so if you actually place the first particle at location R2 and the second particle at location R1, so basically, if you look at the line in black ink and the line in purple ink, the difference is the order of the two coordinates, of the two locations. Okay, and so if you then just go in and everywhere you see an R1, you replace it with an R2, and everywhere you see an R2, you replace it with an R1, you get basically the purple expression here, and what you see then is actually that the two expressions are the same. There's no difference. It's just the order in which those appear is switched, but the final result is the same. And so we can say that switching the two particles around, swapping their locations, makes no difference in terms of the wave function. And so this is what I have here in the red box, is that actually the wave function doesn't care if you put the first particle at R1 and the second particle at R2, or if you do it in the reverse. Makes no difference for the wave function. Okay, and so that here now is an expression of the indistinguishability of the two particles. The wave function just doesn't care if you swap the locations of the two particles. But notice that that only is true with our modified wave function. It wouldn't have been true with our original wave function. Okay. So now, what would happen if we instead of the earlier equation that the wave function doesn't care about the order or the swapping? What if we introduced a minus sign when we swap? Okay, so just imagine if when you swap the two locations of the particles, then a minus sign came in. What would happen then? Okay. So it's a hypothetical question. Would that be a problem for us if it didn't actually happen that way earlier, right? We didn't get the minus sign, but let's just say that we had gotten a minus sign. Would that have posed a problem for us? And we can say that this is also okay. This would have also been okay. The minus sign does not mess us up. And so the question is, why? Why are we okay with a minus sign there? And the answer is actually pretty straightforward. You might have guessed it already, is that in the end, all we can really ascertain are probabilities. We can observe probabilities by repeating an experiment many, many times with identically prepared quantum particles. Okay, and then we get a sense of the probabilities involved. We cannot really measure the wave function directly. We usually only are sensitive to the probabilities. And so probabilities are psi squared. We have to square the wave function. So a minus sign really creeping in here isn't necessarily a problem, because in the end we're going to square the wave function anyway, and so the minus sign would go away. Okay, so even if there were a minus sign in the wave function, then when we square, we basically get the indistinguishability back. In other words, the probabilities don't matter whether we swap the particles or we don't swap the particles. Okay, and so what that thought leads us to is allowing another form of the two-particle wave function. Instead of what we had before, we can also allow this wave function here. So you see that we get here psi A evaluated at R1, and then times psi B evaluated at R2. But now we have minus the reverse, right? So we have minus this piece here. Before we had the plus sign, now we have the minus sign. And you see then with the minus sign, when you exchange R1 and R2 in that expression, you can very easily verify that you get minus the original result. Yeah, so you have now that psi of R1 comma R2 is equal to minus psi of R2 comma R1, and we are going to allow this two-particle wave function as well. These are actually going to be fermions with the minus sign. And what we had before are going to be bosons with the plus sign. So if you're using two identical particles that obey the red box, then those identical particles have to be of the fermion kind. And if you have two identical particles that obey the blue box, then those two particles must be bosons. If you mix and match a boson with a fermion, then you don't need any of these, and you can go back to just, the first equation that we started out with. You don't have to have a superposition then at all. It turns out that bosons have integer spin, so S is equal to 0, 1, 2, and so on, and fermions have half integer spin, so S is equal to 1, 3 halves, and 5 halves, and so on. All the particles that we really, elementary particles that we really come across on a daily basis are spin 1/2 particles. So the proton is a spin 1/2, the neutron is a spin 1/2, the electron is a spin 1/2. The only particle that has an integer spin that we come in contact with on a daily basis is the photon, which has a spin of 1. Okay. We cannot prove this property or this association in this course, but it comes out of relativistic quantum field theory. Okay, so it's a graduate level topic, but what we can prove is the Pauli exclusion principle for fermions. So this only works with fermions. Okay, for the following reason. Well, first, what is the Pauli exclusion principle? We say that two identical fermions cannot occupy the same quantum state. Why is that? Well, let's do proof by contradiction. if two fermions really did occupy the same quantum state, psi A is equal to psi B, same quantum state, then the two-particle wave function would look like this. Psi A of R1 times psi A of R2 minus psi A of R2 times psi A of R1. It's a mouthful. Okay, A and B are basically the same, and so that's what I get, and you can very clearly see that that is going to be 0. So that two-particle wave function would be 0, and therefore it has no probability of occurring. Okay, so we cannot have that. It's not normalizable. If it's another way of thinking about it. It's just 0. And so this cannot happen. Now, you may have heard that, well, we've already used the fact that normally we say that there's 2 electrons that fit into any state, say the states of hydrogen. There's 2 electrons that can occupy the 1s state, the 2s state, and so on, the orbitals. So why 2? Why not just 1? And so there, as we will see, if we account for the spin of the particle, then that is another degree of freedom. So you can actually show later. We can show later that when you include spin, then you can actually have as many as 2 electrons in the same wave function, spatial wave function, I should say, right? The spin wave function hasn't yet been accounted for. Okay, so notice that there is no such problem with identical bosons, because if we had a plus sign there, then that wouldn't add to 0. That wouldn't subtract away, and we would be fine with that. So the bosons do not obey the Pauli exclusion. Do not have to obey the Pauli exclusion principle. It's just fermions. Okay. So here's what I already mentioned, because the state of fermions is not just given by the spatial wave function. It also contains the spinor state, the spin state, the spinor. Then really we have a combined description of the total wave function of a fermion with spin, and now we have two particles that the two-particle wave function that would be given by something like this. Okay, so we have basically what we had before, this psi R1 comma R2. That basically is the spatial part of the wave function, and then now we also have this two-particle spin state, which I'm just labeling chi of 1 comma 2. Okay, so here here is my combined two-particle wave function that is now also including spin. So how does the previous argument sort of change when you also account for spin? We already know what the conclusion must be, namely that now we can get 2 fermions into the same psi state, the wave function, the spatial wave function state. How does that happen formally or mathematically? So for identical fermions, we now know that we have to have this property that psi of R1 comma R2 times chi of 1 comma 2 has to be exactly negative psi of R2 comma R1 chi 2 comma 1. So basically what I'm doing here is when I switch the two particles, not just their spatial locations, but also the spin that they carry, and when I exchange those two particles entirely, I incur a minus sign. Okay, and so that's basically what fermions do. And so they're anti-symmetric under exchange is the jargon, the quantum mechanical jargon. So let's say that we have a spin state by itself that is anti-symmetric under exchange. So that chi of 1 comma 2 is minus chi of 2 comma 1. What would such a state look like? Well, think singlet spin state. We already came across it, right? When we have two particles of spin 1/2, we get an S is equal to 0, M is equal to 0 in this state where up, down, minus, down, up is the combination. And so if you were in such a singlet state and the left particle and the right particle are now exchanged, right, what would you get? Well, do it really quickly. You see that it is actually it's not the same state, right? When you change, sort of just look at it. Just change the two arrows appearing in the two kets, right? You basically see that you're not getting the same state. You're getting the same state only if you then also multiply by a minus sign. And so we can say that we are antisymmetric in the singlet spin state. And so the chi 1, 2 is already minus chi 2, 1. And so then in that case, how do we satisfy the line from before, namely this line here? Well, the minus sign already comes from the chi part of the wave function, and so we actually have to now demand that as far as the spatial wave functions are concerned, they have to be symmetric under exchange. So psi of R1, R2 has to now be equal to psi of R2, R1, such that overall we get the minus sign under exchange, but it comes from the spin state, not from the spatial wave function part. And so here we see that psi A and psi A work, actually, because as far as the wave functions are concerned, we have symmetry under exchange. Okay, so it's almost like it's behaving like boson as far as the spatial wave function is concerned. The minus sign comes from the spin, and so two fermions can actually fit in a single orbital now, in a single wave function, spatial wave function or orbital. Okay, so that's sort of the mathematical reasoning for why that works. Okay, so we have this singlet state where we have two fermions, let's say 2 electrons in the same orbital, but in that case then we do have to have the singlet state, namely M has to be 0, one has to be up, and the other one has to be down because we have to select the singlet spin state. Okay, so we're not allowed to put both electrons in the spin up state and also into the same orbital, like 1s or something. That wouldn't work, right? Because then the spin state would have to be one of the triplet spin states. And now we would have to have the spatial wave function antisymmetric. And now we get the Pauli exclusion principle right off the bat there. Okay, so there we go. Now, with that in mind, we can quickly look at the periodic table. And some of that will spill into the next lecture, but I just want to look quickly at electron occupancies. So in the s orbital, 1s, 2s, 3s, and so on, we have L is equal to 0 and M is equal to 0. We can get 2 electrons in there because we can be in this spin singlet state, spin up, spin down. In the p orbitals, how many electrons can fit there? Well, we have L is equal to 1, and therefore we have 3 choices for M, minus 1, 0, and 1. There's basically 3 p orbitals here with a combined 6 electrons. And whenever you're in a d subshell, then you get 5 choices for M, and therefore there should be 10 electrons that can fit in a d subshell into the d orbitals. I want to stop here and pick it up there in the second part of the lecture. Thank you.